July 3, 1938, Grantham, England. The engineering reports from Continental Railway specialists visiting Britain's most audacious locomotive trials would never capture what they witnessed that summer afternoon. A streamlined steam engine design pushing speeds that defied everything traditional locomotive wisdom said was possible about steam power. Limitations dot through the coal smoke and steam of the London and North Eastern Railway testing grounds. A sleek blue locomotive waited on the tracks using aerodynamic principles that seemed unnecessary to European observers. No exposed boiler pipes, no traditional boxy engine design, no acceptance of the speed barriers that kept steam locomotives safely below 100 miles per hour across Britain's rail networks. Yet, this streamlined machine promised performance with consistency that conventional locomotive methods could not match. In European railway engineering, master locomotive builders required massive boilers that generated power but created drag at high speeds. Each speed attempt beyond 100 miles per hour was considered dangerously reckless by industrial standards. Different boiler pressures, different wheel configurations, different breaking points that no engineer could safely predict. The British were operating with locomotive philosophy the Europeans had never imagined. Practical aerodynamic casing, double chimney exhaust systems, precision wheel balancing, speeds that would challenge not just other trains, but the fundamental limits of steam technology itself. 300 miles from Continental workshops, the most decisive speed revolution in railway history was preparing itself. Not in larger boilers, not in traditional locomotive design, but in the aerodynamic precision that would carry one British engine beyond what railway traditions believed physically possible. Sir Nigel Gresley stood on the platform at King's Cross Station in 1935, watching his latest A4 class locomotive gleam under the station lights. The streamlined casing that covered the engine from nose to tender had cost the London and North Eastern Railway nearly £8,000 beyond standard locomotive construction costs. Railway board members questioned every pound spent on what they considered cosmetic modifications that served no practical purpose. Gresley had spent decades designing steam locomotives, each generation pushing closer to the theoretical limits that physics imposed on steam power. The A3 class Pacific locomotives he designed in 1922 had achieved reliable service speeds of 75 miles per hour, considered exceptional performance for their era. But Gresley understood that Britain's railway future demanded more than reliable service. It demanded speed that could compete with emerging diesel and electric technologies, threatening to make steam power obsolete. German engineers had achieved 124 miles per hour with their streamlined Class 05 locomotive in 1936, a record that stung British pride and challenged assumptions about steam locomotive capabilities. The Americans were developing diesel-electric engines that promised higher speeds without the complexity of steam generation and water management. Even within Britain, critics argued that steam's era was ending, that no amount of engineering refinement could overcome the fundamental inefficiencies of converting coal heat into mechanical motion through water vapor. Gresley's response was the A4 class, a locomotive design that rejected conventional wisdom about what steam engines should look like and how they should perform. That evening, reviewing design specifications in his London office, Gresley calculated performance parameters that would either revolutionize British railways or end his career in spectacular failure. The railway accident at Castlecarry in 1937 haunted every high-speed locomotive discussion in British engineering circles. A standard class locomotive attempting 85 miles per hour on a curved section of track had suffered catastrophic wheel bearing failure. The engine derailed at speed, killing the driver and fireman instantly while destroying nearly 200 yards of track and damaging a signal box. the Board of Trade. Inquiry concluded that steam locomotives operating above 90 miles per hour faced mechanical stresses that existing technology could not safely manage. Wheel bearings overheated from friction at high speeds. Boiler water circulation became unstable under acceleration forces. Track condition variations that trains absorbed safely at 60 miles per hour became deadly hazards at higher velocities. Gressley attended the inquiry hearings, listening to experts explain why his dreams of 120 miles per hour steam operation were physically impossible. Railway mechanical engineers demonstrated with mathematical certainty that wheel bearing temperatures at 100 miles per hour would exceed safe operating limits within minutes. Boiler specialists proved that water circulation patterns destabilized above certain acceleration thresholds, risking boiler explosions that would destroy the locomotive and kill everyone nearby. The testimony that struck deepest came from veteran locomotive drivers who had spent careers learning to read engine behavior through sound and vibration. They described how locomotives began developing dangerous oscillations above 80 miles per hour, frame resonances that could shake engines apart if sustained. These were not theoretical concerns, but lived experiences from men who had felt their engines trembling on the edge of mechanical failure. One driver, Thomas Morrison, described attempting 95 miles per hour during a special mail run in 1936. His testimony was precise and chilling. At 90 miles per hour, the locomotive began vibrating with increasing intensity. At 93 miles per hour, the coal tender started bouncing on its coupling, threatening to separate from the engine. At 95 miles per hour, wheel flanges began striking rail joints with impacts that felt like hammer blows transmitted through the entire frame. Morrison had immediately reduced speed, but the experience left him convinced that steam locomotives had reached their absolute speed limits. The forces involved at 100 miles per hour were simply too violent for mechanical systems, designed in an era when 60 miles per hour represented exceptional performance. Gressley examined the Castle-Carry wreckage personally, studying the failed wheel bearings and twisted frame components. The destruction was comprehensive, but it was also informative. The bearing failure had occurred because traditional lubrication systems could not deliver oil fast enough to prevent friction heat buildup at high speeds. The frame damage resulted from resonance frequencies that conventional locomotive design never anticipated. In his notebook that evening, Gressley sketched modifications that addressed each failure mode. Pressurized lubrication systems that would force oil into bearings under continuous pressure. Frame designs that shifted resonance frequencies away from operational speed ranges. Wheel balancing techniques that would eliminate the vibrations that destroyed Morrison's confidence, but he understood that convincing railway authorities to approve high-speed testing would require more than engineering solutions. It would require proving that every safety concern raised at Castle-Carry had been addressed through systematic design improvements that made high-speed operation as safe as conventional railway service. The wind tunnel at the National Physical Laboratory in Teddington became Gressley's proving ground in 1935. He had convinced laboratory directors to test locomotive models at simulated speeds up to 130 miles per hour, measurements that would reveal aerodynamic forces no steam engine had ever encountered in actual service. Traditional locomotive design treated aerodynamics as irrelevant. Engines operated in open air at speeds where wind resistance represented a minor factor compared to mechanical friction and grade resistance. But Gressley's calculations showed that above 100 miles per hour, aerodynamic drag increased exponentially, consuming power that conventional locomotives simply could not generate. The wind tunnel tests revealed forces that shocked even Gressley. A standard locomotive design at 120 miles per hour EXPERIEN-CED air resistance equivalent to pulling 15 additional passenger coaches. The exposed boiler pipes, valve gear, and mechanical components that characterize traditional engines created turbulence that multiplied drag beyond anything mathematical predictions suggested. Gressley's streamlined casing solution was as radical as it was simple. Enclosed the entire locomotive in a smooth shell that allowed air to flow around rather than through the mechanical components. The design drew inspiration from aircraft engineering, where aerodynamic efficiency meant the difference between flight and failure. Wind tunnel models demonstrated dramatic improvements. The streamlined F4 design reduced air resistance by 35% compared to conventional locomotives at 100 miles per hour. At 120 miles per hour, the improvement approached 50%, effectively eliminating several coaches' worth of drag through shape alone. But streamlining created new engineering challenges that critics eagerly highlighted. The casing trapped heat around the boiler, potentially creating dangerous pressure buildups. Access to mechanical components for maintenance became complicated, requiring removal of large casing sections that conventional designs left exposed. The additional weight of the streamlined shell reduced the engine's power-to-weight ratio, potentially negating aerodynamic advantages. Gressley addressed each concern through systematic design refinement. Ventilation ducts channeled air through the casing to cool critical components while maintaining aerodynamic smoothness. Removable panels provided maintenance access without compromising structural integrity. The casing itself was constructed from lightweight alloys that added minimal weight while providing necessary strength. The double chimney exhaust system represented Gressley's most innovative solution to a problem that emerged during wind tunnel testing. A single exhaust chimney created a low-pressure zone behind the locomotive that increased drag at high speeds. The double chimney design split exhaust flow into two streams that canceled the low-pressure effect while improving boiler draft that enhanced combustion efficiency. European engineers visiting Teddington examined the wind tunnel results with professional skepticism. The French pointed out that streamlining had been attempted on locomotives before without revolutionary results. The Germans noted that their own high-speed locomotives achieved excellent performance, using semi-streamlined designs that retained maintenance accessibility. The Italians questioned whether British track conditions could safely support the speeds that aerodynamic efficiency promised. Gressley's response was characteristically direct. Wind tunnel models predicted performance that actual testing would either confirm or refute. The F4 class design incorporated every aerodynamic advantage that current engineering knowledge could provide. If critics doubted the results, they were welcome to observe the testing that would prove streamlining's value through measured performance rather than theoretical debate. The first F4 class locomotive, number 2509 Silver Link, emerged from Doncaster Works in September 1935. Carrying innovations that represented 3 years of intensive engineering development. Every component had been designed or redesigned to support sustained high-speed operation that conventional locomotives could not survive. Boiler pressure of 250 pounds per square inch exceeded standard practice by 30%, generating steam power that would drive the 3 cylinders with force that traditional valve gear could not efficiently manage. Gressley had developed a valve timing system that optimized steam distribution at speeds above 90 miles per hour, maintaining power output where conventional systems became inefficient. The wheel balancing represented precision that locomotive manufacturing had never previously required. Each driving wheel was balanced to within ounces, eliminating vibrations that would become destructive at high speeds. The balancing process required specialized equipment that Doncaster Works had built specifically for F4 production. Machinery that could measure and correct weight distributions that conventional Methods could not detect the coupling rods connecting. The driving wheels used manganese steel alloys heat-treated to specifications that added weeks to manufacturing schedules and hundreds of pounds to component costs. Railway accountants questioned every expense, but Gressley understood that component failure at 120 miles per hour would cost infinitely more than precision. Manufacturing. Initial testing of Silver Link on the Wanakok King's Cross to Newcastle route in November 1935 exceeded even Gressley's optimistic projections. The locomotive achieved 112 miles per hour during a trial run with a dynamometer car, maintaining speed that would have destroyed conventional engines within minutes. The smooth operation surprised everyone, including the test crew, who reported that the engine felt more stable at 110 miles per hour than standard locomotives at 75 miles per hour. The success triggered immediate orders for additional A4 locomotives. The LNER board, previously skeptical of streamlining costs, now demanded rapid production to capitalize on performance advantages that could revolutionize passenger service. By early 1938, 35 A4 locomotives were operating on Britain's East Coast Main Line, providing service that cut journey times by hours compared to conventional trains. But Gressley understood that revolutionary performance and record-breaking attempts required different engineering priorities. Service locomotives were designed for reliability across thousands of miles of varied operations. A record attempt demanded absolute optimization for a single, high-speed run where every component would be pushed to its theoretical limits. Locomotive number 4468. Mallard, completed in March 1938, incorporated refinements that production of 4 locomotives did not receive. The boiler tubes were individually tested to higher pressure standards. The valve gear was hand-fitted with clearances measured in thousandths of an inch. The streamlined casing received additional polishing that reduced surface friction beyond production specifications. The modifications were subtle but significant. Mallard would not be faster than other A4 locomotives under normal service conditions, but at the absolute edge of performance, where every fraction of efficiency mattered, Mallard represented the pinnacle of what steam locomotive engineering could achieve. In his office, overlooking Doncaster Works, Gressley studied performance calculations that predicted Mallard could reach 125 miles per hour under ideal conditions. The number seemed impossible even to him. Speeds that would make a steam locomotive the fastest it had ever been or ever would be. July 3, 1938. Began with weather conditions that experienced locomotive crews recognized as perfect for high-speed testing. Cool morning air increased engine efficiency by allowing denser steam generation. Calm winds eliminated crosswind forces that could destabilize a locomotive at extreme speeds. Clear visibility would allow the crew to monitor track conditions at distances necessary for safe high-speed operation. Driver Joseph Duddington had been selected for the record attempt based on 25 years of locomotive experience and a reputation for precision that made him legendary among LNER crews. He understood steam engines through intuition developed across thousands of miles, able to hear problems in valve timing or feel power fluctuations through throttle response before instruments could register changes. Fireman Thomas Bray would maintain the boiler pressure that determined how much power Mallard could generate. Firing a locomotive at 120 miles per hour required different techniques than normal service. Coal had to be distributed precisely across the firebox to maintain even heat. Water levels had to be monitored constantly, as the violent motion at high speeds could cause false gauge readings that might lead to dangerous boiler conditions. The test train consisted of Mallard, a dynamometer car to record speed and power measurements, and 6 passenger coaches ballasted to represent a typical express service load. The route was the slightly descending grade south of Grantham. where track conditions and gradient would support maximum speed if the locomotive could generate necessary power. Duddington opened the throttle gradually as Mallard accelerated through Grantham, building speed systematically while monitoring engine behavior. At 90 miles per hour, the locomotive was operating smoothly, the streamlined casing eliminating the buffeting that plagued conventional engines. At 100 miles per hour, Duddington could feel the power reserve still available, the boiler maintaining pressure that indicated Mallard had more performance to deliver. At 110 miles per hour, the world outside became a blur of countryside and signal posts, passing too quickly for normal visual processing. The dynamometer car instruments were recording power outputs that exceeded anything previously measured on British railways. Inside Mallard's cab, the sound was surprisingly quiet, the streamlined casing creating an acoustic environment completely different from conventional locomotives that screamed with mechanical noise at high speeds. At 115 miles per hour, Duddington noticed slight oscillations beginning in the locomotive's frame, vibrations that matched predictions from engineering calculations. He maintained throttle position, trusting Gresley's design to handle stresses that were destroying the middle big end bearing. Even as Mallard continued accelerating, the speed peaked at 126 miles per hour for approximately 300 yards, a sustained velocity that made Mallard the fastest steam locomotive ever recorded. The dynamometer car instruments captured measurements that would be analyzed for decades, proof that steam technology could achieve speeds that every expert had declared impossible. Duddington began reducing speed as planned, gradually closing the throttle and allowing Mallard to decelerate under controlled conditions. The middle big end bearing that had overheated during the maximum speed run was failing, but the damage remained contained. Mallard would need extensive repairs, but the record had been achieved without the catastrophic failure that critics had predicted would result from such extreme operation. The middle big end bearing failure that ended Mallard's record run revealed the true cost of pushing steam technology to its absolute limits. When maintenance crews inspected the locomotive at Peterborough, they discovered bearing damage that would require complete replacement in frame. Modifications to repair properly, the bearing had operated beyond its design temperature limits for approximately 3 minutes during the maximum speed run. The white metal bearing surface had partially melted, creating metal-to-metal contact between the bearing and crankpin that would have caused catastrophic failure if sustained for another mile. The lubrication system that worked perfectly at 100 miles per hour could not deliver sufficient oil to prevent friction heating at 126 miles per hour. Gresley examined the damaged bearing with professional interest rather than disappointment. The failure was predictable, occurring exactly where engineering calculations suggested the weakest component would fail first. What mattered was that every other system had performed flawlessly. The boiler had maintained pressure. The wheels had remained balanced. The frame had absorbed vibrations without structural damage. The streamlined casing had eliminated aerodynamic forces that would have destroyed a conventional locomotive. The repair process required 6 weeks of intensive work at Doncaster Works. Engineers used the opportunity to implement bearing modifications that would prevent similar failures. Though everyone understood that Mallard would never again operate at record-breaking speeds, the locomotive returned to regular passenger service in September 1938, where it would spend decades proving that high-speed capability could coexist with reliable daily operation. Critics immediately questioned whether the record had been worth the cost. The bearing failure suggested that 126 miles per hour represented the absolute limit of steam technology, rather than a speed that could be sustained or exceeded. Conservative railway managers argued that the record attempt had risked a valuable locomotive for publicity that provided no practical operational benefits. European response was mixed but largely respectful. German engineers acknowledged that Britain had reclaimed the speed record that Germany had briefly held. French railway authorities began studying design features for incorporation into their own locomotive development programs. American railways, increasingly committed to diesel-electric technology, viewed the record as confirmation that steam power's era was ending in spectacular fashion. The deeper significance emerged gradually as engineers analyzed the implications of Mallard's achievement. The record proved that steam locomotive speed was limited not by fundamental physics but by specific engineering challenges that systematic design could address. The bearing failure was a component problem, not a systemic limitation. With better metallurgy and improved lubrication systems, even higher speeds might be achievable. But history was moving in different directions. World War II would suspend civilian railway development for 6 years. Post-war railway modernization would favor diesel and electric traction that offered operational advantages steam could not match. The F4 class locomotives would continue excellent service into the 1960s, but they would be the last generation of steam locomotives that British Railways would build or operate. Mallard's record would stand not because later steam locomotives could not exceed it, but because no one would try. The National Railway Museum in York displays Mallard in a place of honor. The streamlined blue locomotive drawing visitors who marvel at engineering achievement from an era when human ingenuity pushed mechanical systems to their theoretical limits. The museum placard notes simply, holder of the world speed record for steam locomotives, 126 miles per hour. July 3, 1938. That record has stood for over 85 years. Not through lack of challenge, but through absence of opportunity. Steam locomotive development effectively ended in the 1960s as diesel and electric traction displaced older technology across world railway systems. Modern preservation groups operate historic steam locomotives, but none pursue speed records that would risk destroying irreplaceable machinery. The engineering principles that made Mallard's record possible remain relevant in unexpected ways. Aerodynamic streamlining techniques developed for A4 locomotives influenced high-speed train design worldwide. The wheel balancing precision that prevented destructive vibrations at 126 miles per hour established standards that modern rail vehicles still follow. The systematic approach to solving high-speed stability problems demonstrated methods that engineers apply to contemporary transportation. Challenges. Several attempts have been made to contextualize Mallard's achievement within modern railway performance. High-speed electric trains now routinely exceed 200 miles per hour, using technology that steam locomotives could never match. But these comparisons miss the essential point. Mallard represented the absolute limit of a specific technology, the moment when steam power achieved its maximum possible performance before physics and engineering. Constraints could impose no further improvement. Load. Tests conducted on preserved A4 locomotives in the 1980s confirmed that the basic design remained sound. Decades after construction, the boilers maintained pressure ratings within original specifications. The frames showed minimal fatigue despite millions of miles of service. The streamlined casings that critics had dismissed as unnecessary decoration had protected mechanical components from weather damage that destroyed conventionally designed locomotives. Engineering students still study Mallard's record run as an example of systematic optimization, achieving seemingly impossible results. The combination of aerodynamic refinement, precision manufacturing, and operational expertise that produced 126 miles per hour demonstrates principles applicable far beyond steam locomotive design. The record represents what becomes possible when engineering excellence accepts no compromises. Sir Nigel Gresley died in 1941, his reputation secure as Britain's greatest locomotive engineer. He never designed another locomotive after the F4 class, recognizing that he had achieved the pinnacle of steam technology. Washington Roebling had continued his father's bridge work, but Gressley understood that steam's future belonged to preservation rather than innovation. The final vindication came through simple longevity that no theoretical analysis could dispute. 85 years after the record run, Mallard remains the fastest steam locomotive ever recorded, a distinction that will almost certainly remain permanent. The streamlined blue engine that experts claimed could never safely exceed 120, and PH proved that engineering vision combined with methodical execution could achieve what conventional wisdom declared impossible. In York, visitors photograph Mallard from every angle, marveling at the machine that redefined what steam power could accomplish. The locomotive sits silent now, but its legacy echoes through every high-speed train that benefits from lessons learned when a British engineer proved that impossible was simply a challenge waiting for the right solution.